very fancy. Okay. Hello, everyone. Today we have Julia. Sorry, I don't know how to pronounce it.
Nakhleh. It rhymes with broccoli. That's what I tell people.
Okay, she's from UW Madison, and she will present the effects of multitask learning on ReLU neural network functions. This work was accepted in URIPS.
Yes.
Right? Okay. Yeah. Congratulations. And Julia is a PhD student here in computer science. Her advisor is Rob Novak, and her interests broadly lie in the mathematical theory of deep learning, and particularly in the mathematical properties of neural networks trained with different regularization strategies. So, Julia, go ahead.
Thank you. Hello, thank you guys so much for coming. Yeah, so like Angeliki said, today I'm just going to talk about some joint work that Joe and I did with Rob Novak, our advisor, exploring the effects of multitask learning on ReLU neural network functions. So in general, our sort of problem of interest is to study the properties of shallow ReLU neural networks, which are trained with weight decay, in other words, to fit data with minimal sum of squared weights. And in particular, we consider multi-output or multitask networks where each output of the network fits a different set of labels, which is corresponding to a different task on the same set of data points. And we wanted to investigate what the differences are in the types of solutions that are obtained using this multitask type of learning problem versus just a single task learning problem where there's only one single neural network output and a single sort of set of labels. So our contributions are that in the univariate input setting, in the case where the data and the input to the neural network is just one dimension, we can very precisely characterize the solutions to the multitask learning problem in this case. And we show in particular that the solution is almost always unique. And we can exactly say the sort of types of data sets of unusual data sets, which would allow for a non-unique solution. And when this solution is unique, it is always given, as we show by the connect the dots interpolant of the data points. And this is interesting because that particular solution, the connect the dots straight line interpolant of data points, is also the solution to a kernel learning problem in a Sobolev type reproducing kernel Hilbert space. And this highlights a connection that nobody has ever found to our knowledge between multitask learning with neural networks and kernel methods. And we also provide some analysis which shows that a similar phenomenon holds in the case where the input dimension to the neural network is arbitrary, not just univariate. And we use the concept of task exchangeability to show more formally that if you have a neural network, a shallow ReLU neural network, of arbitrary input dimension, which is trained on a very large number of tasks, which are sort of unrelated to each other, that this type of problem resembles a particular kernel learning kind of problem. So just to sort of lay everything out, a shallow multitask or multi-output ReLU neural network is just a function from RD to RT, and throughout we just use the capital T to denote the number of tasks, which is synonymous with the number of outputs of the neural network of this particular form, which is parameterized by these input weights vectors WK, biases BK, and output weight vectors VK. And at least in our univariate analysis, we also include this additional affine term AX plus C, which is called a skip connection or a residual connection. And these are commonly used in practice with deep networks. For using in the shallow case, it sort of makes the mathematical analysis a little bit easier and is consistent with some prior research which analyzes neural networks of this form. And in particular, we're interested in neural networks of this form, which fit a given data set and also have a minimal weight decay penalty, which is just the sum of squared input and output weights in the network. And we only regularize the weights, the input and output weights, not the biases. And there is sort of an existing line of prior research which shows that this weight decay penalty is equivalent to the path norm penalty, which is kind of an odd looking at first glance penalty, which is just the sum of products of the Euclidean norms of input and output weights. And because the ReLU function is homogeneous, which essentially just means that you can pull in positive constants in and out of it without actually changing the functions represented, we can, without any additional loss of generality, we can just restrict the input weights to have unit norm. And then the optimization problem turns into this bottom problem where the regularization penalty takes this form, which is reminiscent of a multitask lasso problem. And this is sort of what Joe talks about in his more recent paper. And the multitask lasso is known to exhibit a kind of structured sparsity in solutions. And this is interesting because if you just look at the weight decay penalty, there's no, it's not sort of obvious just by inspection that this would induce any kind of sparsity in the outputs. It's everything looks squared and smooth, but actually it's equivalent to this more sparsity inducing problem. So this is why we call it secret sparsity. So in general, when they're for t equals 1, for just a single task or single neural network output, the solutions to this weight decay problem are generally non-unique. So just as an example, in the univariate case, when there's just one input dimension and one output dimension, for this particular set of data points, which is just the red points here, these blue functions show two different functions which interpolate the data set exactly, but also have a minimal weight decay penalty. And in fact, there are many others as well, including all convex combinations of these two functions would also be optimal interpolants of this data set. And something similar is true in the multivariate input case. It's a lot harder to sort of explicitly prove that any function is an optimal interpolant in the multivariate case, but you can compute exact optimal functions using a convex program. And so this is just a particular example of this kind of pyramid-shaped data set, which has several optimal interpolants. And just as an example, these two bridge functions on the bottom left, which sort of point in opposite directions, are both optimal, and their convex combination, which is this function on the right, is also optimal. So this is just a general fact that anytime for any two optimal solutions in any input dimension, the convex combination of those solutions is also optimal. And this means that in general, there's sort of no reason that solutions to the single task, single output learning problem would be unique. Oops. Sorry. Okay. Yeah. So in contrast, the multitask learning problem almost always has, as we show, unique solutions in the univariate, in the particular univariate case. So in this example that we show, if you just train on this single set of red data points, you could get either this solution on the left, which has this large peak between the data points, or the solution on the right, which is just flat, or many other solutions, but those are two examples. But if you added, for example, a second task, which is represented by these blue labels here, then and sort of trained a two output network to jointly fit both of those tasks with a minimum weight decay penalty, you're now guaranteed to have a unique solution, and that solution is going to be the connect the dots interpolant of both of those data points. And that's true in this particular example, and it's true in almost all examples, and for almost all kind of data sets, as I will talk about in the next slide. So this is just a precise statement of what I just said, which is that, first of all, for any multitask learning problem, one possible optimal solution is just the function is just a network for which each output connects the dots. So connecting the dots essentially is always an optimal solution. And it will be the only optimal solution as long as the data do not satisfy this sort of particular condition, which is essentially that these two vectors, which are constructed using the data, the labels, and the data, those two vectors, in order for there to be multiple possible solutions, two of these vectors have to be aligned, which it's a very particular kind of condition on the data that is really only satisfied if you have kind of redundant scenarios like the data for each tasks are just sort of scalar multiples of each other, or you sort of very carefully handpicked the data to be to fulfill this specific alignment condition.
Just one thing, can you
Yes.
get rid of the thing on top because it's blocking the titles? Press OK.
Oh. Yes. No, you're fine.
Sorry, Julia, can I ask
Yep.
something? So, what if, let's say, these points were all coming from one task? Like, why do you need two tasks?
If the blue and the red points
Yeah.
are all coming from one task,
Like, what's the difference of having two tasks?
because they're meant to share the same X values in this like particular example, so it wouldn't be possible to fit this with two. It's a little hard to tell in the figure, but they're supposed to.
Okay, but what if they don't share the exact same X value?
If they don't share the exact same X values, then it would just be a single, like, there could still be multiple. Let me look at it and see. Yeah, there could still be multiple optimal solutions for this data set.
Sure.
It could still have peaks in between the red points on the
So
top.
the definition of multiple tasks is the same data point that has different labels.
Yeah, it's that you sort of consider label, that now instead of a single label associated to every data point, you have a vector of T labels.
Mhm.
And then each of the T outputs of the neural network fits those T
And-
labels. That's the multitask kind of.
And do the
setup.
labels what's your assumption, the labels, do they need to be discrete or can they be?
They just need to be real valued in this kind of setup, so they don't need to be discrete. They could be discrete, but mostly we're thinking about a regression problem, so they could kind of take arbitrary real valued numbers. They wouldn't necessarily be
So
discrete.
if you have classification with soft prompt, like soft label, sorry, like not probability 1000, but
Mhm.
0.1, 0.9, blah, blah,
Mhm.
would that be a case of your setting?
Yeah, that would be applicable. I mean, it would be applicable. The setting is fairly general. It's applicable to any kinds of labels. Well, any kinds of like numerical labels. So you could use it with discrete labels, but our kind of analysis of like how rare it is that the sort of statement that that the optimal interpolance will always be connect the dots, that is specific. That is not necessarily true if the labels can only take on discrete values. It's only necessarily,
That's why I said soft labels that they cover distribution, like
yeah. If they're not discrete necessarily, then it is also true. So as long as they're, I think I say this on the next slide. So as long as the labels, for example, if they're sampled with respect to an absolutely continuous distribution on Rn, essentially that this sort of special alignment condition is going to be satisfied with probability 0. So if they're sampled with, so if they're distributed according to like some kind of Gaussian or just any kind of continuous, absolutely continuous probability distribution, then with probability 1, the solution is unique and it is connect the dots. If they're discretely if they're kind of sampled with respect to some other distribution, if it's a discrete distribution or something like that, then that may not necessarily be true. But if it's a, yeah.
You can always check. It's very easy to check given your data, whether you have.
Yes. Yes. Yeah.
I also have one question. Can you go back to the slides where you're having this connecting, yeah, for example, this one. So beyond the X1 and the X6, like beyond the domain, how do you like why you're always showing here an extension of your line within the domain?
Yeah.
If you have it set to be like always flat or something, will that change the total like sum of square root norm?
Yeah, that will change it. And yeah, that is kind of an important point. The optimal solution always needs for the neural network problem, it always needs to extend like linearly down this way and that way. Because essentially like if I think I have a slide about this in a minute, but the weight decay penalty ends up penalizing the slope changes of the function, and every sort of the magnitude of it's the sum that it ends up penalizing the sum of absolute slope changes of the function. So if you have the slopes extending linearly outward, it means that you are not introducing any slope changes in the function before the second data point or after the second to last data point. If you set it to be flat outside the data, then you would be introducing an additional change at the first and at the last data point. And so that's why that solution where it is flat outside the data would not be optimal unless the sort of first and second data points are also flat. But otherwise that solution where it's flat outside the data would not be, it would have a higher weight decay penalty. So yeah, it wouldn't be optimal.
Do you train, when you train the deep neural network, do you actually observe that the interpolated function will have a nicely extended?
Yes,
like it will not decaying away when you have zoom out?
No, yeah, it stays, as long as it's trained to a global minimum, which I guess is not generally something that's guaranteed, but it is at least what we observed when we just did like some simulations of this. I have a slide about that. I can go back to this later, but when you do when you run this in experiments, you do see that it always continues to extend sort of linearly in that way. It doesn't like start bending or anything outside of
I'm interested if you zoom out like 10x more, will that be any fading? So because I generally observe that it tends to fade away, like it cannot shoot up directly.
Yeah, I don't think it should, would it? No, it wouldn't, right?
Yeah, if you have a neuron outside of this domain that has a kink outside of where we're plotting, you would see something happening, but there are no more neurons outside of this range.
Yeah.
Like there are no neurons being activated outside of the range that we plotted here.
Yeah.
So
If they were, they would be, if there were more neurons outside of the range here, they would be adding to the cost of, they would be adding to the weight decay penalty, but not at all contributing to the ability to affect the data points, which is why there can't be any that are like outside of the range of the data.
Yeah. If there were, then you wouldn't be at a global minimum.
It wouldn't be a minimum, yeah.
It would affect anything.
Yeah, so the fact that in this multitask learning scenario that that the optimal solution is almost always unique and it's almost always connect the dots between consecutive data points is interesting because it brings up a connection to a particular kernel learning problem. So specifically, it's a learning problem over what is called the first order Sobolev space, which is this function space H1 that just contains all functions from the interval of the data x1, xn to our real valued functions, which are absolutely continuous and whose first derivative is square or integrable over the data. And it has been shown in some old work from the 60s that this space is itself a reproducing kernel Hilbert space with a particular inner product and reproducing kernel. And this inner product induces a norm, which essentially penalizes the square integral of, or the integral of the squared first derivative. So the L2 norm of the first derivative of the function. And it turns out that the connect the dots interpolant just on the range of the data is the unique minimum norm interpolant of any given data set in this particular reproducing kernel Hilbert space. So this is kind of interesting because it highlights just a particular instance of a connection between a kernel type learning problem and a neural network learning problem, which has never been discussed to our knowledge. And the optimal solution I set in this particular case, if we're only really considering the data, sort of what happens between the first and last data point, then the solutions are the same. If you expanded this range, the optimal solution to the kernel problem would be flat outside of the data points, whereas the neural network one would not. But on the range of the data points, the solutions to the neural network multitask problem and to this kernel problem are the same. Okay, and so yeah, just in order, I'll just go a little bit over the strategy for the proof of how we prove this result. And it relies on the fact that univariate shallow ReLU neural networks are continuous piecewise linear functions where each sort of slope change in the function corresponds to a particular neuron. And the x coordinate of that slope change is given by negative bias of the neuron divided by input weight of the neuron. Here we're still assuming that the input weights are normalized to have unit norm, just for convenience. And then in this case, the location of the neuron is determined by the input weight and bias. And the slope change of the neuron is given by the output weight of the slope change of the function at that sort of knot, you would call it, is determined by the output weight of the corresponding neuron. And so what this means is that the regularization cost, as we consider it, which in this particular case is just the sum of absolute values of the output weights, is equivalent to the sum of the absolute slope changes. So this is why, for example, an optimal function can never have any neurons which are located outside of it always has to be extending linearly outside of the data points, because if you had a slope change somewhere outside of the data points, it would mean that there's an extra neuron there, which is introducing an extra output weight that is not necessary to interpolate the data. And that would sort of mean that the whole thing is not optimal. So viewing univariate ReLU neural networks through this lens of continuous piecewise linear functions and their sort of magnitudes of the output weights as the magnitudes of the slope changes, that allows us to sort of prove the result, as we stated, that the multitask solutions are almost always connect the dots by using the following reasoning, which is essentially you could suppose that by contradiction that there is some solution which is optimal, which interpolates all the data and is optimal for the multitask weight decay problem, and that it has some neuron which is introducing a slope change which is not just located right at the data points. And we would say that that slope change, that neuron is located at this point x tilde, as I noted it in this figure. And then you could just view the output of any individual output of the neuron as the function around this point, and you can kind of denote the slopes as they are in this figure. And then it turns out that just using the triangle inequality, the slopes, the sort of total cost of the network when it looks like this, and it has this neuron at x tilde, is always going to be worse or equal to the cost when you just remove that neuron and would connect x1 and x2 tilde with a straight blue line. And that just falls out of the math shown here, which the inequality just comes from the triangle inequality. And that triangle inequality is always going to be strict unless the sort of vectors of the corresponding slopes for each of the outputs, A minus B and B minus C, satisfy this particular alignment, are aligned. It needs to be the case that A minus B and B minus C are aligned in order for this reduction to not be strictly better. Otherwise, removing that extra neuron is strictly better. So that's where this alignment condition of the data comes from, that essentially, unless your data are aligned in this very specific way, that you could take any neurons which are not located at the data points and remove them, and the cost will always, the sort of representational or regularization cost, aka weight decay penalty, is always going to be better. It's always going to be improved by removing
I
that.
have the question that if you have your y value of the x tilde to be right line on that aligned line, will that, but you have that extra neuron over there, will that cause extra cost?
That neuron would not be, if you have a neuron there, but then the function that's being represented is just like this, that you could just remove that neuron and keep the, and you would still have the same function, but then that neuron is, but then you've reduced the cost. So in this kind of setup, we're sort of implicitly assuming that, like, given that you always have the neural network which represents this particular function in the most efficient way possible. So, for example, like you would never have a neuron which is doing something like that, where it's like located at this x tilde value, but then it's sort of the resulting function is still just lying on this blue line. That would never be optimal for the weight decay problem, because it would just mean that that neuron is just sitting there contributing to the cost, contributing to the weight decay cost, but it's not actually contributing to the function at all. It's not allowing the function to interpolate, to fit the data any better. I don't know if that makes any sense.
I mean, if I guess if you have that extra point sitting right on the line, then the B minus A will be 0, if I understand.
Yes, that's right.
And then C minus B will be,
C minus B would be non-zero.
which is
This whole setup is sort of assuming that wouldn't, like, such a network would never be optimal for the weight decay problem anyway, because if this neuron was lying on this blue line, it would just mean that there's an extra neuron in the neural network. So it's like that like you could just take that neuron away. The function would stay exactly the same. And the weight decay penalty would be better because you just removed a neuron, but the function is exactly the same, so you wouldn't have been affected your ability to fit the data.
So yeah, even though like now if in the data set there is an x tilde that's with y tilde being on the line, then you can still remove that data point. Like the data point is,
oh, if there's a data point there, you still wouldn't need a neuron. You still would need a neuron to be located there, though. Like if you just had a neuron located, you could have a data point on that line, but if you just had a neuron, which is like located here, and sort of is adjusted so that it's just equivalent to this blue line, that would be sufficient. You don't need to have an additional neuron located at the data point. And in fact, you never would, because it would be, so if the data points were like here, and then another data point right there, you would never have a neuron located right there in your optimal solution, because you could just fit them all with a straight line with a neuron located here. And then that would be better than fitting them with two neurons, basically. Like if you can sort of fit them, if they always lie in a straight line, you could fit them all with just one neuron. You would never want to, because that's always going to be worse than just doing it with one. So if this, but to be clear, this X tilde is not necessarily the location of a data point. It's the location of some slope change in the network function. So that's like, we're not necessarily interested in just looking at sort of places where the data points are. We're trying to specifically say, suppose that this X tilde is the location of a slope change in the network function, but it's not at a data point. Then you can say it would be better if we just removed it. And then the result is that almost always the best thing you could do is just connect everything with a straight line, basically. I don't know, does that help?
Yeah.
Okay. Okay, and yeah, I kind of already showed this, but we did some numerical experiments to verify in the top. This is just the result of training a single output neural network with weight decay penalty to fit this red data set. And as you can see, you could end up with multiple solutions between these second and third data points. These are just some examples. Those are all global optimal solutions. On the bottom, we are training now a neural network with two outputs, where the first output is still fitting these red points, but the second output is fitting data points with the same X value. They're not shown on the graph, data points with the same X values as the red points, but now the Y values, the labels are just Gaussian. And if you do that, then you always get the connect the dots function. So by adding a second task and a second output, where the task is in this case just fitting random labels, but there's many types of labels it could be fitting, then you've sort of restricted yourself to always getting this unique solution. Yeah.
Yeah, so I guess the one reason we did this experiment was just because there's a lot of talk about implicit bias of gradient descent and blah, blah, blah. And this is sort of showing that gradient descent isn't really biasing you towards any one particular solution. You can get a lot of variety. And standard standard regularization techniques like weight decay won't be able to distinguish between these three solutions. But now if you do multitask learning, it's sort of like acting as an additional regularizer. It's constraining you to a particular type of minimum norm solution.
In those implicit study of the SGD, do they include the weight norm in the objective function or no?
No, usually not. They're trying to say, like, if I just train for loss, what kind of solution will I get? But I mean, if there's some, yeah, that's a good question. But the idea here was just to say that gradient descent can give you anything. It doesn't really bias you towards any one solution.
Yeah, it depends it could depend on, on just like nuances in the randomness or initialization, or if you use different algorithms, like I think I tried a little while ago, just using your path prox thing, that tends to give you more often this peak solution, but that still varies. So it's just depending on the like nuances of what happened in your random initialization or some weirdness within the algorithm, within the gradient descent. If for just the single task case, you could end up with any one of these solutions on the top or other solutions.
Can I ask again something? Why do you need the multiple tasks for this to happen, right? Because, like again, interpolating extra there, why is it optimal? Like, yeah, why does the multitask? Like, what's the intuition that the multitask induces that behavior? Because like, you could say that, you know, you're again minimizing the norm in any case.
Yeah.
So that should happen smaller norm than the other one, right?
Yeah, so it turns out, so both of these functions, the connect the dots function, as well as all of the ones on the top, have a minimal sum of absolute slope changes, it turns out. So the norm, the norm you're considering is the sum of absolute slope changes, then the ones on the top are as optimal as the one for single output case. The ones on the top are also optimal, as optimal as the ones on the bottom.
But it seems like you have extra slope changes there, or is it?
They all add up over this interval. They all add up to the same thing essentially because this, so yeah, so you have extra slope changes inside the interval, but then that's compensated by having like smaller magnitude of slope changes at those data points. So here you have no slope changes within the interval, but then you have these sort of fairly steep slope changes at the red points. Whereas here you have this really steep one in the middle, but then not very much at the data points. That's why they're all the same. That's why they're all, yeah, they're all optimal in terms of having minimum sum of absolute slope changes. So in the, yeah, in this univariate case, there are a lot of instances you could construct. This is just an example, but there are a lot of instances you could construct where it needs to be basically the requirement is that the sort of data needs to, the concavity of the data needs to be like consistently concave up or concave down. And then on this middle interval, you could have many, just for the single output case, you could have many different possible solutions. But once you've added a second output, the intuition is essentially that that's doing weight decay with multiple outputs encourages each output to rely upon the same set of neurons. That's something that's discussed more in Joe's paper. But also you still sort of want the sums of slope changes of each of the individual outputs to be small. And so a lot of times for a lot of different data sets, really the only way to do that, to have sort of every output share the same set of neurons, but also be kind of small, is just for everything to be connect the dots. That's sort of an intuition behind why the multitask, yeah, why adding additional tasks sort of forces everything to be connect the dots. Okay, so it's a little harder to say something quite as precise about what happens in the case where the inputs to the neural network are dimension greater than 1. But we can still say something. And so here we kind of drop the skip connection in the neural network formulation, more or less because it's not really necessary for the analysis, although I believe all the results should still hold if you added a skip connection to it. And now instead of so in the univariate case, we mostly focus on the interpolation problem. So the network needs to exactly fit the data. Here we sort of expanded this to just consider any regularized loss problem where the loss doesn't really need to satisfy any assumptions except for that it needs to be low or semi-continuous in its second argument. And that's just required in order for this problem to be well posed for there to be a minimum. And yes, and everything we have here is also, so we consider this sort of more general formulation where you're minimizing the loss plus a penalized regularization term. But everything we have here is also applicable to the interpolation problem, which is just the limit as lambda goes to 0, which just corresponds with minimizing this sum of output weight norms subject to the requirement that you interpolate your data. So this is a slightly more general type of problem to consider.
What is Bohr's semi-continuous?
It means that it's like continuous, but it basically means like this. It could have a jump, but if it looks like that, then it's still, that's sort of sufficient for it to have a global minimum. You could, if you wanted, just say that the loss function is continuous because that's what most loss functions are. But
What is the meaning of Bohr here? Bohr.
upper semi-continuous would be like this.
Oh, okay. In terms of function value.
It would be, it has to do with the limit, I'm trying to remember, I think the definition is that, yeah, is that the limit from the bottom basically has to be realized here. rather than here.
Mhm. It's like one-sided continuity.
Yeah.
Yeah, okay, yeah, okay. And since we're minimizing, we need lower. Minimizing, okay.
Yes, if you were maximizing, then you would need upper, but.
Okay,
Yeah.
got it.
So the sort of intuition guiding our analysis and the of what happens for multiple tasks and multiple input dimensions is just that if you sort of imagined that you had a neural network fitting a large number of tasks, and each of the tasks are unrelated to each other, just in the loose sense that they don't have like special relationships or correlations among them, you might intuitively think that every neuron would be contributing to a lot of the different tasks because they're sort of all very different. You wouldn't just have one contributing to one contributing to another. And in this case, that would sort of mean that if you just looked at the optimal output weight corresponding to a particular neuron and a particular task S, that would be relatively small compared to the sums of the magnitudes of the optimal output weights for that same neuron, but for all of the other tasks, excluding S, because we're assuming that the tasks are that there are a very large number of tasks. So the output weight for any individual one would intuitively be small compared to all of the others. So if this is indeed the case, then just by a Taylor series expansion argument, this L2 norm of the output weight vector VK would be approximately equivalent to this sort of quadratic term on the right. And that just comes from the Taylor series expansion of the function square root of x squared plus c squared, for which the remainder is if c is very, very large, then the remainder of that function, the sort of higher order terms become very small and the quadratic term dominates. So according to this kind of loose argument, it seems reasonable to think that if there are a lot of tasks and they're all very different, then the regularizer of the neural network problem, which is the sum of norms of output weights, if we sort of look at it from the perspective of an individual task, that it would sort of resemble this quadratic type function. And we can make this reasoning a little bit more precise using the concept of exchangeability, which is just an idea in probability, which is that a sequence of random variables, you would call it exchangeable if the joint distribution of the random variables is invariant to permutations of the indices of the variables. So on an intuitive level, it sort of means that the order of the random variables itself doesn't matter. In particular, IID random variables are exchangeable. That comes from just the fact that the joint distribution is the product of the marginal distributions if they're independent, but there are exchangeable sequences which are not necessarily independent. And an example, a really simple example would be like sampling without replacement, where it's not independent because each sort of sample affects the remaining events, but it is exchangeable because the order in which the sort of items were removed from, if you're sampling like balls from a jar or whatever, if the order in which the specific balls were removed doesn't matter. So that's kind of an intuitive way to think of exchangeability. And also as in that case, as in any exchangeable, in order for random variables to be exchangeable, they do have to be identically distributed. They just might not necessarily be independent. So as a particular example, so we're specifically interested in the label vectors being exchangeable, which basically means that just the vectors of labels corresponding to each task are exchangeable across the tasks. And so, for example, if you just sort of randomly selected a set of T probability distributions and distributed each label vector for the specific tasks according to the corresponding probability distribution, that would be an example of exchangeable process that would generate these, that would result in these vectors being exchangeable. Yeah.
I'm sure I understand that.
Yeah. It's complicated. Yeah.
Yeah, let's. Yeah. Can you like,
Which part? The exchangeability or this specific example of?
no, I mean for the labels, the parts for the labels.
Yeah.
So you say you assume vector labels?
Yeah, essentially what you want is that you want to consider vectors of labels, but instead of considering the vector of all of labels corresponding to an individual data point, you want to consider the vector of labels corresponding to a specific task. So that would be, it would be a vector with n things in it. And it would be, if like for task T, you would take the label corresponding to data point 1 task T and then data point 2 task T, and you just put them all in a vector, and it's a vector of n elements, and you have T of them,
Okay,
if that makes sense.
yeah, and so what does it mean to be exchangeable now? So you have aggregated over your data set the labels?
Yeah.
And you mean in terms of in what order the model sees them, like?
Yeah, essentially, yeah, you want it to be the case that that if you just sort of arbitrarily relabeled, like renumbered the tasks, the joint distribution would be the same.
Okay, so it has to do, so you don't change only the labels, you change basically take the data point with the label, right? And you say if I saw them in a different order, it wouldn't matter. Is that correct? Or- Because if you
Is
only
that correct,
change.
Joe?
So think about it like you have these y semicolon 1, that's a vector, right? And it's
Yeah.
n-dimensional, you have t of them. Now, if I have t row vectors, right? If I do any permutation, the joint distribution of those vectors doesn't change. That's what it's
And
changing.
permutation in the column space.
In the rows, I permute the rows. So imagine each row, so row 1 corresponds to
So
y,
you basically just say it doesn't matter in what order I will see the tasks.
basically.
Yeah, basically, yeah, yes.
Columns are firstly exchangeable, right?
Columns are, you're independent across the columns because you're IID sampling. You assume the data points are. Yeah.
So
So
these are
you're-
so
Yeah.
exchangeable.
Although I don't-
Exchangeable,
I don't think that is required in our,
yeah,
I mean,
but
you could assume that, I don't think you need to, though.
yeah.
And so it has to do like in terms of it won't change something in the output of the model, like is it an assumption over training or is it an assumption over?
This is an assumption about the data. This is an assumption that the data needs to satisfy. It's not an assumption of about the model or the training process. It's that the labels for the data, like the given labels in the data set, need to satisfy this.
In this thing, we're
Assumption.
taking like a probabilistic perspective. We're assuming the data is sampled from some distribution. It's different from the first part.
Yeah,
And I think we have like 5 minutes.
yeah. Let me just see. So essentially what happens is that if you make this assumption about the labels being exchangeable, you can formalize the argument that I talked about previously using the Taylor series, and you can show that the objective function, if you just view it as sort of everything in the optimization is fixed, except for the output weights corresponding to this particular task, you can show that that objective function is approximately equivalent to this quadratic objective function H, near the minimizer V star of the first objective. And yeah, I wanted to include a figure about that, but I didn't. But this all just kind of says that that is true. And that is interesting because this quadratic objective, which I just rewrote. Yeah, so it shows that minimizing the original objective is under the assumption of exchangeability approximately equivalent to minimizing this particular quadratic objective. And now because this is quadratic, there's like a squared penalty here instead of not a squared penalty in the original one. This minimization can be related to an L2 minimization over a fixed kernel determined by the optimal features. That's the like 30-second summary. Yeah, these are just some details about that. I don't know. Do you have questions?
So is there any assumption on distance between tasks?
On what do you mean by distance?
So you said unrelated tasks, many unrelated tasks.
Yeah.
But the definition of unrelated should be formalized as.
Yeah, the definition of unrelated in this case is exchangeable, more or less. That is our way of, there are certainly many ways that one could think of tasks as being unrelated and try to formalize that. But in this case, we were specifically wanting unrelated to mean that they don't have particular correlations among them. So like a very strong example of that would be if they're independent, for example. But it turns out that anything you can say about when they're independent, you could also say just about when they're exchangeable. So it can be stated more broadly, but exchangeability is essentially our way of formalizing the idea that they're unrelated. They may not be totally unrelated, but they're sort of only loosely correlated to each other, if that makes sense.
So can you explain everything in the high level of what this then you end up with implies? So like
Of what this
how-
H
yeah.
is, yeah. So basically, we showed that if you just take the original neural network objective, view it as only dependent on the variables, only a function of the variables corresponding to any individual task, then you can use the properties of exchangeability and show that that objective function is approximately equivalent to this other objective function H. And now if you look at this objective function H, it's the data fitting term is the same. The thing that's changed is the regularizer. And now the regularizer, instead of looking at this L2 norm across all of the tasks, it is a quadratic type of regularizer where each of the output weights are being squared in the regularization. And so that particular regularization, you can relate there and just there's a constant factor before each of the squared weights. But you can relate that to, if you just sort of write it in that form, it looks like a weighted L2 regularization. And you can relate that to, and that is equivalent to a problem of just minimizing this sort of weighted L2 penalty over a fixed feature matrix, which is determined by your optimal neurons. So the idea is that with this, when you have multiple tasks, you're sort of, everything is still dependent on what your optimal neurons are, but a single task training problem is equivalent to training this sort of L1 type of minimization over your optimal neurons, whereas multitask training problem is like training a weighted L2 regularization over your optimal neurons. The optimal neurons themselves may differ, but within the set of optimal neurons you have, you're encouraging like a different type of linear combination of those neurons in your solution.
So what if you were to train with, very to regularization in the single task case? Like, is it the difference, does the whole interpolation thing stems from the model implicitly have this gamma parameters? Or is it like, what if you were to just train with like, would you get the perfect interpolation, or is it something?
If you were to just train like this problem, but without those constant?
I mean, you go to the single task and you just train with a different regularization.
Mhm.
Which regularization, the one you're using the multitask. The one you ended up in the multitask case.
Then
And then would you see, like, if you run this experiment, will you see the same interpolation? Like, is it about the regularization that the data don't interpolate?
if you ran it, if you did this with the same regularization, then you would get solutions, which are, if you did a single task, but explicitly did it with a regularization that resembles this multitask thing, then you would get a solution similar to the multitask solution.
Those are we have some of those experiments too. We have
Yeah.
on like small scale of problems, but you see it kind of visually. Yeah, so like what this is sort of saying, so the top problem is really a kernel problem. It's a Hilbert space problem, and it's unique and it's well studied. The bottom problem is very akin to a lasso problem,
For arbitrary data sets, it's non-unique and corresponds to fitting over a certain Banach space. And this is what people understand to be what's going on with neural networks. They say, oh, it's associated to a certain Banach space, that's the function space associated with neural networks. And what we're saying is, well, when you have the neural network do multiple things at once, each individual thing is really doing something closer to like a kernel rate compression. No longer doing this Banach space thing.
And I think that's all. The rest of the slides are just details specifically about what Hilbert space that the L2 regularization corresponds to, but yeah. So yeah, does anyone have any more questions?
Thank you.